Good afternoon, everyone. I'm Chaoxian Qi from University of Houston. Today I will talk about the DNN-enabled real-time modeling of EM LWD responses in complex subsurface formations. This is my outline. I will first introduce the background and motivation. Then I will discuss some detailed methods we used in this presentation. After that, I will show some simulation results. Finally, I will draw the conclusion and give some possible future work. Electromagnetic logging is an essential technique for formation evaluation because the EM wave is sensitive to resistivity. As you can see in this figure, the logging tool goes down in the underground formation. The produced EM wave by the tool will interact with the formation. The EM field is received by the tool. The reflected wave can be used to estimate the resistivity of the formation. Finally, we can make the decision of the wheel trajectory based on the logging data. For example, we can determine the location of the gas, oil, rock, and etc. The logging tool used to acquire measurements in our study is configured with one transmitter and two receivers. The work frequency range from 2 kHz to 100 kHz. When the tool operates, a 9-component tensor of the magnetic field can be obtained, based on which the measurements for inversion can be calculated following the standard formulas. So there are 4 measurements, and each one is sensitive to different properties of subsurface formation, which means the formation geometry and properties can be extracted from the measurements. So the question is, how can we do that? The subsurface formation can be very complex. For example, there are several typical formations: pinch-out, fault, and unconformity. So the 2D or 3D inversion is necessary to recover the complex subsurface formation based on the tool measurements. And there are 2 key elements of inversion. The first one is accurate fault modeling, which can calculate the tool responses. And second one is the effective inversion algorithm, which can reconstruct the formation from the measurements. Let me first introduce the conventional fault modeling. We use the finite difference method. So the fault modeling is mapping from the model parameter to tool responses, including the attenuation, phase shift. The model parameter is a vector of resistivity, permittivity, and other parameters that can describe the formation. The fault operator is defined by the governing equations. Those are Maxwell equations. So for each computation of the fault modeling, it takes about 4 minutes. Then I will briefly talk about the inversion. The inversion is an inverse procedure of the fault modeling. So we have the measurement data, and then we can use this measurement to figure out the model parameter. So this could be realized by solving a optimization problem. Here, we just formulate the objective function as this. The first term is the data misfit, and the second and third term are the difference matrix to impose the smoothness penalty along the horizontal and vertical direction. This method has some limitations, so it's very computationally expensive and time-consuming because it calls the for the modeling several hundred times. So sometimes it will take several hours to do the inversion task. So it prevents real-time data interpretation and subsurface calculation. So let's review the limitation of the traditional method for modeling the logging tool. It is time-consuming for the modeling and also for the inversion. So we propose a fast modeling diagram which is based on a surrogate model. So you can see in this figure, when we have the formation property, we don't use it for the finite difference method. We just use the surrogate model to directly get the tool response. In this presentation, we use the deep neural network. The deep neural network is known as strong capability of extracting the mapping between input and output. So once the neural network is trained, it can calculate the tool response in milliseconds, and so it can achieve the real-time inversion. For example, when you have the input, and then we just train the neural network, and then we can get the output. This is the tool response. So this is the workflow of the fast modeling framework. So there are three modules. The first one is a classification. So when we have a rough resistivity distribution, we can determine the formation type, such as a parallel layer, fault, or unparalleled layer, using the classification. The second module is the parameter extraction, which can figure out the model parameter that can describe a certain type of formation. And the third one is the surrogate. As long as we get the model parameter, we can calculate the tool response by the surrogate model. In this slide, we just show three types of formations. The first one is the parallel layer. It can be described by 6 parameters. And the second one is the fault. It can be described by 9 parameters. And the third one is the unparalleled layer. It has 7 parameters. In the first module, we use the ResNet to do the classification. It is essentially a convolutional neural network that has 18 layers. The input of the network is model image. The output is a class of model. We use 20,000 images as the dataset for training and testing. So the performance of the neural network can be evaluated by the confusion matrix. If the pre-processed image are used as input, the accuracy can reach 100%. Therefore, we suggest pre-processing the dataset before training the classification network for a higher accuracy. The second module is the parameter extraction. Using the same dataset, the second deep neural network is trained to extract the model parameters. The input of the network is model image, and the output is a vector of parameters. In this table, we just show the model parameters for 3 different formations. Here we define a mean absolute error to evaluate the performance of the network. We observe that the results are reasonably good. So the third part is the surrogate model. So given the formation parameter, we can calculate the tool response using the surrogate model. So we built the second model using a deep neural network. It contains offline training and online prediction stage. In this presentation, we take the fault as an example. It has 9 parameters. So we first generate 40,000 data using the 2.5D finite difference method. Then we train the neural network such that it can predict the tool response given the model parameter. And this is the structure of the neural network. This slide shows the simulation results. Here we test the two models. The color denotes the resistivity. The right figure just shows the tool response obtained by the surrogate model and the rigorous modeling. So we can find the good agreement. This table just shows the computational cost. So we can find the surrogate model takes less than 5 milliseconds. However, the 2.5D rigorous simulation takes around 140 seconds. So this indicates the high efficiency of the second model. Then we use the second model to test the inversion. This figure shows the ground truth. It is the true model we used. The color denotes the resistivity distribution. This figure shows the inversion. Based on the surrogate model, we can find they almost have the same distribution. And this is the inversion results using the 2.5D finite difference method. And this is the initial model to get the final inversion results for this one. So if we compare these two results, we can find the surrogate model-based inversion is more accurate. On the other hand, we can find the surrogate model is much more efficient than the conventional inversion because the surrogate model takes less than 2 seconds. However, the conventional inversion takes more than 3 hours. Here we have some conclusions. First, a general framework is proposed for fast modeling the EM logging tool, and the deep neural network for 3 modules are trained and tested. The second model can fast approximate the tool response with several milliseconds, and the surrogate-based inversion can predict the fault structure using several seconds, and it has higher accuracy than the conventional inversion. So in the future, we will build the surrogate models for the other formation types such as water cooling, parallel layered formation, and etc. So we would like to acknowledge the support by the U.S. Department of Energy, Office of Science, and Office of Advanced Science Computing Research. So that's all for my presentation. Do you have any questions? Thank you.